Hi, this is Mark Weitzman. Welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. Today I want to continue some theory in our group theory and physics course. And it's been a while since I recorded a video. A lot's been happening in the world. I've been very busy in the market, and just reading the news is taking up a huge amount of my time. But it's time to get back to some physics. So I'd like to start today. This will be, we'll be doing Schensted's book, Part 2, Chapter 1. We'll be continuing with the theory on the Frobenius or group algebra. And this will be a video. I think I'm going to break it up into two videos. So this will be video 5A. Basically, we'll cover simple matrix algebras. And for reference, see section 1.6 of Schensted book, which is on my website for the group theory and physics in the resources section. Okay, and also my notes on Schensted's book. Okay. So you might have to review some material, but I'm just going to briefly recap. Previously, we multiplied the projection operators rho k c c prime by group elements we have a group G. Usually we call the set of group elements, let's say A, I. This is a set. I equal, looks like a sum sign. I don't know. It's a group equal to I equal 1 up to n elements in the group. And we started by multiplying by the group elements on the left, and we obtained a left ideal. And we had a decomposition of the group algebra the group algebra is A of G. This A has nothing to do with the group elements AI, other than it means the group algebra. And we wrote it as the sum from k equal 1 to r of L1k plus L2k plus dot 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 L lambda k. So just to briefly review the notations, the L's are left ideals. R is equal to the number of irreducible reps, and lambda k is the dimension of the kth irreducible rep. Now the thing is, this decomposition as we showed in some earlier videos is not unique. So basically, if we set k equal 1, if we set k equals some specific number, that's the kth irreducible representation, we can reduce that rep into lambda k ideals, but how we divide this up here is not unique. And that can be a problem. Now, if instead we multiply the projection operators on the right, then we get right ideals. Let's call them R. And if we go further, and multiply projection operators on the left and right, then we get two-sided invariant ideals. And the decomposition becomes AG is equal to V1 plus V2 plus ... VK. And so each VK is a two-sided ideal spanned by lambda k squared elements, rho k c prime. C and c prime, there's two indices, they both go from 1 to lambda k, that's why we get lambda k squared elements. And this decomposition is unique. And by unique, obviously each of these spaces is invariant, but we could use different basis elements. We can always use equivalent representations and basis elements. So, but this is what's important. And not only that, they form, or they are, a simple, the VK, simple matrix algebra. So let's define what we mean by a simple matrix algebra. Definition. A simple matrix algebra, we abbreviate it as SIMATALG, of dimension alpha squared, is an algebra where we have alpha squared basis elements, EIJ, I comma j equal 1 comma 2 dot 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 alpha, and they satisfy eij ej prime L is equal to the Kronecker delta del jj prime. Remember, this is 1 if j equals j prime and 0 if j is not equal to j prime. Not rho, I'm sorry. EIL. I comma j comma, this is for all indices, j prime comma L equal 1 comma 2 all the way up to alpha. Okay, so each element using this, remember, a general element of the algebra will be a sum of coefficients times the basis elements. So each element x equal to the sum ij, xij, eij. We can associate that with a square matrix. We'll denote that by xij. And it is easy to show from the definition that if we multiply elements of the algebra z equal xy, this is algebra, elements of the SIM ATALG, this occurs if and only if the matrix Z is equal to the matrix X times the matrix Y, or ZIK, using the usual definition of matrix multiplications, sum over J, Xij, Yjk. So this is why it's called a simple matrix algebra. Now, the following facts are easy to establish, and if you can't establish them, then I suggest you read the book. So 1, the alpha elements E1M, M equal 1 comma 2 comma alpha. And this will be true. I used 1, but basically what we're saying is, fix the row, and so for anything, fix the first index, and they span a left ideal. And similarly, EM1, that's a 1, M equal 1 up to alpha, span a right ideal. More importantly, the elements, or as a consequence of that, EMM, this is going to be both a left ideal and a right ideal. So this is in LM intersect RM. Again, M equal 1 comma 2 all the way up to alpha is a primitive idempotent. This is very nice. And you might want to refresh your definition of a primitive idempotent. It means that its square is equal to 1, and it cannot be broken up into two other idempotents which square to 1 and which are mutually annulling. That's what makes it primitive. And then finally, for the element, not finally, we'll have 5 things. Let's call it epsilon, E11 plus E22 plus dot 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 E alpha alpha satisfies any element of the group algebra, not group, any element of the matrix element. So this is an element, I'm using this just in a element of simple matrix algebra. XE equal to epsilon x, and so this is equal to the sum over ik xik eik, and so it commutes. So this special element here commutes with every element of the simple matrix algebra, and so that's nice. And so this element is an idempotent, but it is not primitive. As you can see, it's the sum of a whole bunch of primitive idempotents, and it's called the modulus of the simple matrix algebra, and it behaves like the identity element in the simple matrix algebra. And we can show that any element which commutes with every element of the simple matrix algebra must be a multiple of the modulus epsilon. So I'm going to stop right here. I've decided to try and make these videos shorter, but I'm going to, in the second video, I'll transfer these results back to the projection operators and derive an orthogonality. I'm not going to derive it, but I'm just going to write down an orthogonality relation, an expansion relation, and a dual orthogonality relation, which we'll probably use later. Now you might be thinking, what is the use of all this stuff? Well, this is theory that we'll need when we do when we start analyzing permutation groups, which will be very important for understanding the general linear groups and special unitary groups and orthogonality groups. So this will play a role in elementary particle physics, things like, I don't know if you've heard when we cover it in chapter 3, Young diagrams and representations of the symmetric groups are extremely important. And we'll find operators that will be like these modulus, and we'll have things like simple matrix algebras. So I'll see you next time. Thank you for watching. Bye-bye.